All right. Now, we already know that when you're talking about simple harmonic motion is usually defined by the equation A equals to negative omega square x. This is what you know as the defining equation of SHM. Now, in a lot of cases, when you look at your questions for systems that undergo simple harmonic motion, they may be described using other equations. The motion of that system oscillating may be described using other different equations. Okay, but at the same time, because that system is undergoing simple harmonic motion, it must obey the defining equation of SHM, where A equals to negative omega square x. So to do questions like that, usually what you will have to do is that you compare the given equation with the defining equation of your SHM, and then after that, you'll be able to work out certain answers out of it. All right. So let's just say, for example, you have a pendulum bob here. The pendulum bob oscillates, it undergoes SHM, but then we tell you that the motion can be described by this equation where AL equals to negative GX. So what you want to do is that you want to change this equation in such a way that it is comparable to A equals to negative omega square x. So here what you will do is that you try to make A the subject, and you make sure that x is at the other side of the equation here, so that you get A equals to negative GL over x. So once you have that, you can now make a direct comparison between this equation and A equals to negative omega square x. So from here, maybe it would be better if I try to write it out here. If A equals to negative G over Lx and A is equals to negative omega square x, you can actually make a direct comparison where you say that negative G over L is equals to negative omega square, or rather omega square is equals to is equals to G over L. You just omit out the negative. Okay, so here you can find out what is your omega, your angular frequency is actually the square root of GL. If you then want to find out what is your frequency, you just expand out omega to become 2 pi f, such that you can actually find out your frequency now. And if you have wanted to, you can also expand it out to find out your period, where you just replace frequency as 1 over t, so that eventually your t is equals to 2 pi square root Lg. Okay, so depending on what your question wants, you have to change your questions, you have to change the equation accordingly. All right, so another different example here could be your mass spring system. Again, this time we tell you that your mass spring system, it oscillates, but the motion is described by equation ma equals to negative kx. You change it in such a way that is comparable to A equals to negative omega square x. So right now, you compare A equals to negative k over mx and A equals to negative omega square x, you can say that omega square is actually equals to km. From which you can do the same thing, find out what is omega, find out what is frequency, or find out what is your period. Okay, so this is a common thing that you have to learn how to do in your exam questions. So to start it off, there's some questions on there that you can do. This one should be page 19 of your worksheet. Now, if you look at page 19 of your worksheet, this one is March 2017 P42. If you look at that question now, you have a uniform beam that is clamped at one end. A metal block of mass m is fixed to the other end of the beam, causing it to bend as shown in figure 3.1. If you look at this diagram, you'll notice it's actually the same diagram as the previous question that we just did, okay? But the question that they're asking now is entirely different thing. The block is given a small vertical displacement and then released so that it oscillates with simple harmonic motion. The acceleration A of the block is given by the expression A equals to negative km x, where k is a constant for the beam and x is the vertical displacement of the block from its equilibrium position. Explain how it can be deduced from the expression that the block moves with simple harmonic motion. So you want to deduce out from this expression that your system is undergoing simple harmonic motion. So one thing that you can do usually, there's always a standard working here that you follow. If you consider your spring constant, this is not spring constant, the K is just a constant in itself. The tell K is a constant, and then you look at your mass M. Your mass M is unlikely to change during the oscillation. It's also going to remain constant, isn't it? So if you look at the expression K over M, you can say that K over M is constant. So acceleration A is directly proportional to displacement X. This is the first criteria. And then after that, you also notice that there's a negative sign in your expression. The negative sign here indicates that acceleration and displacement are always in opposite direction. So hence your motion is going to be simple harmonic motion. Okay. So you notice that there's a certain pattern here of answering when it comes to proving from equation that something follows simple harmonic motion. You always need to say what is constant first. In your case, this thing here is constant. Only then can you say that A is proportional to X. And then after that, you always make sure to single out the negative sign. The negative sign tells you that A and X are always in opposite direction. So when you have those two criteria, it is therefore simple harmonic motion. Okay, so that's one thing to note from there. All right, then after that in part B, for the beam, K is 4 kg per second square. Show that the angular frequency omega of the oscillations is given by this expression. So this one here, all you just need to do is that since they've given you an equation to describe the motion, compare it with simple harmonic motion equation. So you get this first equation here, compare it with the second equation here. You can say that eventually after comparison, omega square is equals to Km, such that omega is square root K over M. And then after that, you just submit your values of K is 4, but you square root it becomes 2 over square root M now. So this one is shown. Okay. Then after that, you move on to the following part. They mentioned to you that the initial amplitude of the oscillation of the block is 3 centimeter. Use the expression in B to determine the maximum kinetic energy of the oscillations. The expression in B that you just use is omega equals to 2 over square root M, if I'm not mistaken. Is it? Yeah, that's the expression that you had. So they want you to use it to determine the maximum kinetic energy of the oscillations. So when it comes to maximum kinetic energy of oscillations, we already did know that KE max is going to be half m omega square x naught square. This one is going to be your total energy also lah. All right. But here we just want to specifically think of it as your KE max. So K max is half m omega square x naught square. You want to find the maximum kinetic energy. You know the amplitude from there, from here. But do you know the omega? The omega, you will notice you don't actually know the exact value. And do you know the mass? The mass is also unknown here. All right. If you just look at the equations here as it is straight, you will notice that you do not know the mass, you do not know the omega, you cannot possibly proceed from there. So there's something else you need to do with this equation here. The hint is already from what the question mentioned here. Use the expression in B. So what you really needed to do was that if you recall omega is 2 over square root m, you sub it inside here, you will get half m multiplied with 2 over, this 2 squared, 2 over m, times with your amplitude of 0.03. So even though you do not know the masses, it's not an issue because the masses cancel. So eventually you will get your answer as 1.8 times 10 power minus 3 joules. Okay, the working is actually shown here already. All right. The ones that is being shown on the left-hand side here is really just a derivation showing you kinetic energy maximum is half m squared omega squared x naught squared. This is actually not necessary to be shown. You don't always need to derive it out. You just need to say KE max is actually half m omega squared x naught squared, and then just follow through with your working. Okay, so this one is for this one. Then if you move on to the next question, there's actually two different ways to do this question. So the next question says that over a certain interval of time, the maximum KE of oscillations in C is reduced by 50%. It may be assumed that there is negligible change in the angular frequency of your oscillations. From there, determine the amplitude of oscillations. Okay, so right now, there's actually two different cases to consider. You had the first case here, and you had the second case here. All right. So for both cases, you're still talking about the maximum kinetic energy. The thing that links both of them together is the maximum kinetic energy equation, where you say it's half m omega squared x naught squared. So for both cases, you can actually say that the mass is still the same. The omega is also the same because the question specifically mentioned it here to you. There's negligible change in the angular frequency. So m and omega are constant here. That tells you that KE max is proportional to the amplitude squared. So if you want to find out the new amplitude oscillations, you can say that KE max 2 to KE max 1 is equals to amplitude 2 square over amplitude 1 square. So KE max 2 is actually half of the original one, so it's 0.5 over 1. And then your original amplitude was 3 centimeter, change it to meter is 0.03 square. What you want to find is the new amplitude. Okay, so you solve this equation here is 0.5 times 0.03 square and then square root 8. You will get your answer as 2.12 times 10 power minus 2 meter. Okay, this one is by you using a ratio method of doing this. Now, there is another different method too that you can use. This one is the one that is written in red. This one may be a lot more straightforward because you'll see your question says that your maximum KE is reduced by 50%. That means your KE2 is 0.5 of KE1. So this one you can actually just say is half m omega square. You can actually use the expression that you have here originally. Make your life simpler. It's actually half, sorry, not this one, the second one. Your EK max can be reworded as this once you substitute out the omega, right? So this one is actually just going to be half kx naught squared equals to 0.5 times 1.8 times 10 power minus 3. This k here, you substitute as 4, and then you work through your workings. Your x naught will eventually become 2.12 times 10 power minus 2 meter. It's going to give you the same thing. Okay, so the method is actually summarized right over here. So this one may be easier for some people because a lot of people I noticed they don't like to use ratio because for some reason they find it to be tedious. So you want a more direct, easier method is the one that is written in red here. Okay. So you now have a look at page 15. This is November 2016 P41. In this question, to demonstrate simple harmonic motion, a student attaches a trolley to two similar stretch springs as shown in the figure here. Your trolley has a mass of 810 grams. The trolley is displaced along the line of the two springs and then released, and the subsequent acceleration of the trolley is given by this equation here, where spring constant K for each of the springs is 64 Newton per meter, and X is the displacement of your trolley. Show from there the frequency of oscillation of the trolley is 2 Hz. So whenever you see a separate equation being given for a simple harmonic motion question, almost always you have to compare with your defining equation of SHM in order to work out some sort of answer of it. So here you again compare the two equations. Once you compare them, you can make a conclusion saying that omega squared is 2k over m. Okay, and because they want frequency here, all you just need to do is you sub out the omega as 2 pi f. So the omega as 2 pi f, square it, equate it to 2k over m. Okay, and then after that, sub in all your values. Okay, so frequency is square root of 2 times 64 divided by 0.81, then divide by 1 over 2 pi. Okay, your answer eventually will give you 2 hertz, just like that. Okay, then in part B here, they say that the maximum displacement of your trolley is 1.6 centimeter. Calculate the maximum speed of your trolley. Okay, what's the maximum speed of your trolley? So Vmax is, as mentioned before, is omega x naught. Okay, so right now, they already did tell you your maximum displacement of trolley is 1.6 centimeter. This one will be your x naught. This is your amplitude. Your omega is not given, but you do know the value of your frequency. So frequency as before, just sub it out as 2 pi f, multiply with x naught. You have the full complete values in your question already. So it's 2 pi times 2. The 2 is from here. That is the frequency. And then multiply with your amplitude of 1.6 centimeter, change the meter. You will get Vmax at 0.201 meter per second. This one is your final answer. Okay, so again, this is a pretty straightforward question to do. Then after that, you go on to the next particular question. Now, in the last part of your question, they say that the mass of the trolley is increased and the initial displacement of the trolley remains unchanged. Suggest the change, if any, that occurs in the frequency and the maximum speed of the oscillations of the trolley. Okay, so this one, the question just asks you to suggest the change. They didn't really ask you to explain why the change is like that. Now, some people can use common sense here. They use their own common sense where they say that because the mass of the trolley is increased, is somewhat heavier, so it becomes slower. So therefore, your period increases. The time taken for you to complete one oscillation increase, then frequency decreases. And also because it is slower, this means your max speed is lower too. This is the logic that some students tend to use, because the moment they see that the mass has been increased, it's heavier. It should move slower. So if it moves slower, max speed is obviously lower. And if it's moving slower, you are taking a longer time to complete one period, so your frequency will drop. So therefore, your answer is frequency decrease and maximum speed decrease. Okay. So, but if you want to have a proper way of deducing these answers here, you can actually refer to the equations that you were originally given. The initial part of the question mentioned to you that your motion is described by this, but you eventually show that omega squared is equals to 2k over m. So that omega squared equals to 2k over m that you did can be related to your frequency, where you say that it is 2 pi f squared equals to 2k over m. All right. So now, from this equation here, there are a number of things that are constant. Your k is constant, your mass is constant, your 2 pi is obviously a constant. So that eventually you can say that F squared is inversely proportional to M. Okay, so here you already have a relation between the mass and frequency. If you know that your mass has increased, this will tell you your frequency will drop. So that will explain your answer at the top here. This one is by looking at the equation itself. Then how about the part where you talk about your maximum speed? So your maximum speed, Vmax is equals to 2 pi f x naught. They told you that the initial displacement of your trolley remains unchanged. This one actually implies to you that your amplitude remains constant, okay? Because initial displacement of your trolley remain unchanged. So here, Bmax equals to 2 pi f x naught. If amplitude remains unchanged, x naught is constant, that would mean that Vmax is proportional to f, because there are two constants here inside the equation, x naught and 2 pi. So Vmax is going to be proportional to frequency. In the earlier part of your workings here, you already did say that frequency drop. So here, if Vmax is proportional to frequency drop, Vmax must also drop here. So this one would explain why your second answer is like that. Okay, you can deduce it from your equation. In addition to using some simple common sense here, sometimes the common sense method works, sometimes it doesn't. All right. Okay, now if you have a look at page 27 of your worksheet, this one is November 2017 P42. Okay. So the first two parts of the question is actually something that we've done before. So this one will just go through it really quickly. So 3A1, define radian, is actually from circular motion. Define the radian is asking you to define the unit of 1 radian. Is angle subtended at the center of a circle where the arc length is equals to the radius. This is from circular motion. We've done the question on this before. And then for 2, state by reference to simple harmonic motion what is meant by angular frequency. Angular frequency is frequency expressed in terms of radians per second, or you could write it in words, angular frequency is equals to 2 pi times frequency. Okay, either one would just be fine. Now, look at part B again. This one is like a repetition question in terms of the pattern. Here they tell you have a thin metal strip clamped horizontally at one end that has a load of mass m attached to its free end. The metal strip bends, as shown. When the free end of the strip is displaced vertically and then released, the mass oscillates in a vertical plane. Theory predicts that the variation of the acceleration A of the oscillating load with displacement x from its equilibrium position is given by this equation here, where L is the effective length of the metal strip and C is a positive constant. Explain how the expression shows that the load undergoes simple harmonic motion. So again, it is very similar to what we've just done before. You are supposed to deduce from this given equation that your object is undergoing SHM. So there's always a standard pattern to answer this. You always need to say what is constant first before you move on to saying that acceleration is directly proportional to displacement. So here, what is constant? You need to specifically identify it out. Here, you need to say that C over ml cubed is a constant, which you can actually verify to be true. They already said to you, C is a constant. L is the length, which should not change. And then M is your mass, which also by right should not change. So all of these are actually your constants. If you combine them together, they will obviously still be a constant. So C over ml cubed is constant. Acceleration is directly proportional to displacement. This is one point here. And then the other thing you just need to say is that because there's a minus sign here or negative sign here, the minus sign shows that the acceleration and displacement are in opposite directions. This is your other point here, okay? So once you have those two, therefore the load is undergoing simple harmonic motion. You actually don't need to write this last statement here. You really only need to have the first two statements. Okay. So this one is for part one, right? So in part two, they mentioned to you that for a metal strip of length L 65 centimeter and load of mass M 240 grams, the frequency of the oscillation is actually 3.2 hertz. Calculate out the constancy. All right, so this one you have to make a direct comparison of your given equation with defining equation of SHM. So you compare the first equation with defining equation of SHM, you will get a conclusion saying that C over ml cube is equals to omega square. So you want to change out your omega into 2 pi f. Square it, equate it to C over ml cube, and sub in the rest of the values that you know. Okay, so frequency is 3.2, mass is 0.24, length is 0.65. Find out what is C. C is actually 26.6 kg meter cube per second square. Right? So that is for this question. Okay, now I will look at page 33. This one would be June 18 P42. Okay, state two conditions necessary for a mass to be undergoing simple harmonic motion. This one we went through it quite a fair bit of times already. For something to be classified as simple harmonic motion, your acceleration must be directly proportional to your displacement. Okay. And secondly, your acceleration must always be directed towards a fixed point. You could word it in another way where you say that displacement and acceleration are always in opposite directions. This one is the more common one. Okay, the one that's written in red. Okay. Okay, so if this one is okay, then you move on to B, part B. Now, a trolley of mass 950 grams is held on a horizontal surface by means of two springs attached to fixed points P and Q as shown in this figure here. Okay. Then after that, they mentioned to you that the springs, each having a spring constant of K 230 Newton per meter, are always extended. The trolley is displaced along the line of the springs and then released. And then after that, the variation with time t of the displacement x of the trolley is as shown here. Okay. This one is the oscillation of your trolley. They're showing the displacement with respect to time. And then after that, they ask you this. This one was something that I haven't really taught, so I'll start teaching this. They ask you, state and explain whether the oscillations of your trolley is heavily damped, critically damped, or lightly damped. Okay. Now, what can you see about your oscillation right now in terms of the amplitude? Now, when you are generally talking about an oscillation, where we tell you you are interested in the graph of displacement versus time, you typically would expect it to be something like this, where your amplitude is constant. This one is an ideal case where you have no energy loss. When you have no energy loss, amplitude remains constant. Okay. Well, what if you have energy loss? This one is more for your actual case, real life case. If you have that same displacement versus time graph, x versus t, a lot of times when you go and look at your real life oscillations, the amplitude doesn't remain constant with time. It actually tends to decrease with time in a manner similar to this. So here you see in terms of the amplitude, this point, this point, this point, as well as the points below, your amplitude is actually decreasing. This one is more for your actual case. Okay, not the ideal case. There is energy loss. Okay, when you have energy loss, your amplitude decreases. Okay, there's energy loss, so your amplitude decreases. In your AS physics, you will have learned that energy is actually tied to amplitude. Remember, in AS physics waves, we always tell you intensity is proportional to amplitude square. And then after that, intensity is actually energy per unit time per unit area, or in other words, power per unit area. So if you have energy loss, you have power loss, it will affect your amplitude. So in real life cases, you actually have energy losses, so your amplitude will drop. So right now, you are seeing for your current diagram, the amplitude is actually decreasing, but very slowly. You can see that from here to here and here to here, the line actually is curved, or rather diagonal or slanted. All right, the amplitude is decreasing. There is energy loss. Now, specifically, what we'll mention here is that energy loss in oscillation is known as damping. Okay. All right. When you have energy loss in oscillating system, that is known as damping. They ask you to still explain whether the oscillations of the trolley were heavily damped, critically damped, or lightly damped. Okay. So when you look at the graph itself, you notice that the oscillations is actually still maintained while the amplitude decreases. So this one is going to be light damping because the amplitude decreases gradually, or the oscillations still continue, so there's light damping. Okay. If it was critical or heavy, you won't see the oscillations. It will just straight away return to equilibrium. Okay, but in your case, you see oscillations continuing, it is therefore light damping, or you can actually revert it as amplitude decreasing gradually, so it's light damping. Okay, now what are the causes of this damping? Just now I told you your damping is actually energy loss from your oscillation, and the energy loss from your oscillation is actually due to the fact that you are doing work against resistive forces. Your resistive force could be friction, your resistive force could be air resistance. But here you need to be specific for your question. What are the sources of resistive force for your trolley? So your source of resistive forces could be the friction between your wheels and your surface. Okay, so the cause of your damping here is loss of energy due to friction between the wheels and your surface. Okay, you can say this. The damping is due to loss of energy due to friction between wheels and surface, or you can actually also say loss of energy due to friction in the wheels itself. When the wheels are trying to turn, it's in contact with your car body, right? So there's friction there also. Or you can also say it's air resistance, but it's less common here. Okay, so either one of this. Now for part 2, they mentioned this. The acceleration A of the trolley of mass m may be assumed to be given by this expression. May A is equals to 2k over m times x. Calculate the angular frequency omega of the oscillations of the trolley. So again, you are given some sort of equation. You already know by now you need to compare with simple harmonic equation, A equals to negative omega square x. So you compare those two together, you will get a conclusion stating that omega square is 2k over m. So from here, you know all the values. Omega square is equals to 2 times 230. This is the value of k given in the previous page. Your mass is also given in the previous page. It was given as 950 grams, if I'm not mistaken. So change it to kg. Your k was given as 213 Newton per meter. So sub that in, you eventually get your omega as 22 radians per second. Okay, pretty straightforward, isn't it? Then the last one, determine the time t1 as shown in figure 4.2. Okay, now time t1 is this particular point here. Now, if you look at the graph carefully, this is one period. This is 1 period t. If you extend it a bit further, from here to here, this is actually half a period. So overall, T1 would have been 1.5 T. So you need to find out what is your period in the first place. Okay. So what you can do is something like this. You already found out the value of omega in the previous question. Try to find T from there. So omega is equals to 2 pi over T. You sum in the values, you eventually get T as 0.286 seconds. All right. Then I already mentioned to you that T1 is 1.5 of the period. So multiply with that, you will get the answer as 0.428 seconds. Just like that. Okay.